When an autonomous vehicle navigates a dense urban intersection at dusk, it has to track stochastic targets, objects moving with highly unpredictable trajectories. To maintain safety, 6G networks use the ISCC paradigm. ISCC stands for Integrated Sensing, Communication, and Computing, an architecture where vehicles no longer operate on separate spectrum bands for radar and data, but instead execute both functions simultaneously using shared hardware. Macroscopically, this network relies on multi-antenna base stations serving a fleet of single-antenna vehicles. Each base station is equipped with a mobile edge computing server. MEC is a network architecture that brings computational power closer to the physical location of the user, allowing vehicles to offload heavy processing tasks rather than relying entirely on their internal hardware. If we zoom into a microsecond-level time slot, the cycle begins with the ISAC signal transmission. ISAC uses a single radial waveform to bounce off targets like radar and carry encoded data to the base station. In the sensing phase, the echo returns, and the vehicle's local CPU must immediately pre-process this raw data to remove clutter. At the exact same time, the vehicle initiates communication, offloading the computation-heavy analysis back to the MEC server. These three distinct functions, radar sensing, data communication, and algorithmic computing, are all forced to share an identical temporal slot and the exact same physical hardware. That overlap creates a highly constrained, multi-dimensional bottleneck. The first absolute boundary of this system is the vehicle's total power budget, represented mathematically as P max. The vehicle only has a strict finite amount of wattage to distribute across its systems. To detect targets accurately, the radar requires high transmission power to increase the echo SINR. SINR stands for Signal to Interference plus Noise Ratio, a metric that compares the strength of the desired radar echo against the sum of background noise and interfering signals from other vehicles. But routing more power to the antenna incurs a severe local computing penalty. Every watt pumped into the transmission signal cannibalizes the energy available to drive the vehicle's local CPU frequency, extending the time it takes to pre-process the data. There is also a communication penalty. If multiple vehicles in the same geographic area aggressively scale up their transmission power to improve their own radar, they create severe co-channel interference. That interference degrades the data offloading rate for everyone trying to reach the base station. The engineering objective is to minimize the maximum task completion latency across all vehicles in the network, while strictly maintaining a hard target detection probability threshold, meaning the echo SINR cannot drop below a specified limit, gamma d. The physical reality dictates a zero-sum game. Optimizing any single physical parameter locally, like boosting power for better radar, inherently degrades the network's global computational performance. We translate these physical constraints into a mathematical objective function to minimize maximum latency, TK. Inside are highly coupled variables, subband allocation matrix A, transmit power vector P, receive beamforming vector U, and CPU frequencies F. Combining binary logic with continuous variables creates a complex min-NLP formulation. The system must solve this formulation within a microsecond time block before the CSI degrades. CSI stands for Channel State Information, representing the known scattering, fading, and power decay properties of the radio link at any given millisecond. Because vehicular mobility changes the physical environment instantly, calculating a brute force global optimum is computationally impossible in the time allowed. We have to use a technique called alternating optimization. To solve the MNLP, the framework systematically decouples the variables. It slices a monolithic equation into 4 isolated, independently solvable mathematical layers. The first layer isolates the discrete variable, the binary subband allocation matrix, A. Every permutation of frequency subbands assigned to vehicles can be mapped as an L-array search tree. To navigate this, the algorithm uses a breadth-first search, scanning across all possible subband assignments at the top layer before moving deeper into the tree. Checking every single node takes too long. To prevent infinite search times, the system runs a background algorithm to establish a global lower bound. This acts as a pruning mechanism. If an allocation branch drops below the minimum radar threshold, it is instantly eliminated. By combining the search tree with aggressive pruning, the system solves the integer logic of the MNLP, securing optimal spectrum allocation within the microsecond timeframe. With the subbands locked in place, the system drops to the second layer, solving for the continuous variables of transmit power and local CPU frequency. The obstacle here is the offloading rate constraint. The relationship between power transmission and data rate forms a non-convex curve, making direct optimization impossible. The algorithm handles this using successive convex approximation, replacing the hard-to-solve non-convex function with simpler convex approximations. First, auxiliary variables break the constraint into manageable pieces. Then, a first-order Taylor expansion linearizes the feasible region, mathematically flattening the geometry into a convex polygon. The system solves this linearized region, updating the constraints and iterating the process until the power levels converge on an optimal value. That leaves only the final two continuous variables, the edge CPU frequency allocated by the base station and the receive beamforming vector. Neither of these requires complex iterative approximation. The mobile edge computing power is allocated based on a strict fairness criterion, which yields a direct closed-form equation that the server can execute instantly. The receive beamforming vector is reduced into a generalized Rayleigh quotient. The optimal antenna array direction is mathematically extracted by finding the generalized eigenvector corresponding to the maximum eigenvalue of the interference matrix. By sequentially navigating discrete search trees, linearizing non-convex curves, and extracting eigenvalues, the system resolves the intractable MINLP in a matter of microseconds. We can see the material impact of this alternating optimization algorithm by looking at the empirical data it generates. This chart shows the resulting subband allocation matrices across three specific schemes: a computing-centric approach, a sensing-centric approach, and the optimized joint design. The colored nodes represent individual vehicles sharing the same frequency block. Look at the sensing-centric allocation. By forcing orthogonal subbands for all nearby vehicles, it effectively eliminates radar interference. But because it groups vehicles with vastly different channel qualities onto the same frequencies, it severely penalizes the offloading rate for vehicles furthest from the base station. Now look at the joint design layout. It maintains radar orthogonality for neighboring vehicles to preserve target detection, but it dynamically groups vehicles that are similar distances from the base station, which equalizes the channel quality and optimizes the MEC offload. If the network optimizes purely to maximize the radar's echo signal, it degrades the vehicle's real-world reaction time by bottlenecking the edge computation link. This chart shows the maximum task completion latency under varying raw data compression ratios. As the volume of data generated by the radar increases, the network is subjected to extreme stress. For networks using fixed power allocations or sensing-centric designs, the latency scales exponentially. Their processing times spike rapidly as the data volume climbs, but the joint design line remains flat across the bottom of the graph. Because the decoupling algorithm precisely balances the subband assignments and the local computing power, it successfully absorbs the penalty of massive data offloads, maintaining low real-world latency regardless of the radar's heavy demands. In a stochastic, multi-agent vehicular environment, optimizing for a single metric like offload speed or radar clarity is a trap that inevitably forces a system failure somewhere else in the network. True latency minimization in a ISCC ISCC network requires mapping physical hardware constraints directly into multidimensional matrices and systematically convexifying the edge cases.